Welcome to Deep Learning Adventures, everybody. Thanks for joining us tonight, and those of you that will be joining us later on our YouTube channel, thanks for tuning in, and we will hopefully see you live in person in the future. I'm going to go ahead and share my screen, and hopefully you can see everything. If you're not familiar with our group, we're called Deep Learning Adventures. We've been meeting for over a year now, virtually, via Zoom, and we try to hold an event about every once a week. We cover different courses on deep learning and machine learning, as well as do deep dives into coding. And occasionally we're joined by some of the authors of the courses or other people who are experts in the field to do an interview. If you look on our meetup page, you can see some of the prior things we've covered. And we also have several of our different courses hosted on YouTube in some playlists that are listed here. We have a very active Slack group, and there's a link to join it on our meetup page, or we'll post it here in the chat later. And for tonight, we're going to be covering part 2 of a specialization through Coursera that was developed by Deep Learning AI. And I just want to give attribution to them for some of the material, a few graphics you may see, or code snippets from their excellent course. And we want you to, if you haven't already, check it out and maybe consider joining along with us and taking it or one of their other excellent courses. So we want to give them a shout out. So what are we going to be talking about? Well, we've been starting this TensorFlow Data and Deployment Specialization, which is offered by Coursera. It was developed by deeplearning.ai, and it involves 4 different courses. The first one goes over TensorFlow.js, and we just completed that last week. And now we're ready to dive into TensorFlow Lite. And if you haven't already looked at what that course covers, it's made up of 4 weeks. The first one is an overview of the TensorFlow Lite library from Google and everything you can do with it. Then we're going to go into some very practical hands-on development of some models. The first one will be Android, and the third week will cover iOS. And then the last week, we'll actually talk about edge devices and such. In this case, it's actually going to be a Raspberry Pi. So looking forward to hearing about all of that. Week 1 is going to be covered by George Zoto. No, I'm sorry, I think I have that backwards, right? Week 1 is going to be covered by Robert Craig, and then week 2 will be George Zoto. So with that, I'm going to go ahead and turn it over to Robert to begin for us.
All right, now I am not muted. Can you hear me and see my screen?
Yes.
Yes. Wonderful. So to start right where David left off, we'll be beginning the device-based models with TensorFlow Lite course tonight. And as David mentioned, there's week 1 is mostly general considerations regarding deployment to edge devices and phones. And then in weeks 2 and 3, we talk about Android and iOS systems. And then in week 4, we'll get onto the edge devices. Let me go ahead and move this down a hair so I don't get Zoom interfering with my mousing, if I can. Or I'll just use I think I can just use these buttons to move around. So week 1 here, I'm going to loosely stick to the order of the original videos. We get kind of an overview of the entire course here at the beginning. And then we'll go into very general considerations on machine learning models and how those considerations intensify or change as we want to move to using these machine learning models in mobile systems and embedded systems. And then the further we get down, we get a little bit more into the weeds, more into code itself. So we do the take a look at the saved model format. This, I think it's called take a look at the saved model format, but it's really more a section that's about the conversion process itself. And as part of that conversion process, we'll be talking about optimization of a model, which includes quantization, among other things. Then we'll get a little bit deeper and we'll talk about running models on mobile devices. And at that point, the course starts to run through screencasts, and I'll walk through the notebooks with a couple of examples from this first week's worth of material. And hopefully when we're done with that, we'll be ready to think about deploying them to specific systems, such as the Android, which George will be covering here shortly. So at the beginning of this week, we had the conversation, as typical, between Andrew and Lawrence. And I really enjoy many of these conversations. They give you a high-level perspective of the important aspects of the course, why we're even studying the course, but sometimes there's some amusing stories as well. And as both of them are clearly tech people, they each recounted their own experience and the joy of the first time that they were able to produce models that could detect things like fruit. In this case, we're not only detecting the objects, but we're also putting bounding boxes around them, so it's localization as well. And Andrew recounted that he showed this model to a friend of his who was not a developer, and the immediate reaction was, well, okay, but I already knew that was a banana. So what is this going to do for me? So it's kind of funny, but I think it does illustrate a greater point that we as developers need to keep in mind the greater picture while working on technologies. I think there certainly could be many uses for the banana detector. I could certainly envision, especially during the pandemic, but even before in general, wouldn't it be great to send a robot to the grocery store for you to pick out these things, walk through the produce aisle, and detect what a banana is and pick it up for you, and maybe even recognize which ones have too many brown spots or something on it. So that was one application that they shared. Another pretty cool application that they mentioned that we'll be looking more towards later in the course is a little miniature self-driving car that Lawrence has built here, and he's shared with Andrew, and just describing how he's got a little Raspberry Pi right here on the top, and he's running TensorFlow Lite in order to detect lane markings and basically to run a whole reinforcement learning type algorithm on the car itself. You've got a little camera up here attached to this Raspberry Pi, and as you drive, you're collecting data about the positions of the steering and where the car is ending up. And he indicated that this system was quite successful, at least in a very highly controlled laboratory environment. So it was kind of fun for a software guy to be able to play with something like that. So in very, very small scale.
Robert, for the benefit of anybody that's considering taking this, you mentioned deployment onto Android, iOS, and then this Raspberry Pi. Are you required to have those to take the course?
That is an excellent question. There's a lot of different technologies required and different hardware that is implied as we go through the course. One really nice thing about this course is that all of these hardware and software environments that would be needed to deploy these things to actual systems are emulated in one way or another in the course. So week one, we'll just be talking about general considerations, and I'll be using Jupyter Notebooks and Python exclusively. But for week two, there are Android simulators that you can use for deployment to the Android system. There is also an implication that it would be helpful for one to know a little bit of the Kotlin language, the Android development environment, be a little bit familiar with that. But the course is organized in such a way that you really don't need to know any of that. Really, the prerequisite here is knowing enough Python and enough TensorFlow to understand what these models are doing. All the other languages, such as the JavaScript that we encountered during the browser-based course the last couple weeks, and all the different ecosystems we'll be playing with here. iOS will be working in Swift, and there will be an iOS and Apple iPhone emulator as well, and then there will be an emulator for the Raspberry Pi too. So you can work through all the materials in the course without having those systems on hand, any of that hardware. I imagine it's more fun to actually implement it on real hardware, but it's not a requirement for the course. Thanks for the question. And by the way, I know that it's very small here, so it might be obvious with the fairly small crowd this evening, but please feel free to interrupt at any point with questions. I hope that this is very much a multi-way discussion. As mentioned earlier, we are just now working through the course ourselves, so we are certainly far from experts in this material, but we're hoping to share this learning adventure with you, and so please feel free to participate however you are comfortable this evening. It's always helpful to have feedback and questions and an engaged room. So moving on a little bit further into the materials from the course, we also have a GitHub repo, which is provided by Deep Learning AI, who authored the course, and this is all through Lawrence's repo, Lawrence Moroney, the author of the course, who has been collaborating with Andrew Ng. And all 4 weeks, all the materials that you'll need for the course are here. So even if you're not enrolled in the course with access to the videos and graded exercises, you can still actually work through all these materials here. And it's pretty well self-contained, although it's certainly helpful to have the videos explaining what's going on. There's also a guide at tensorflow.org/lite that goes into far more detail on most of the topics in this course than we will, but it's a useful reference, and I'll point to it a handful of times this evening. So I think let's move on to some considerations when moving machine learning to the edge and to mobile AI devices. So this slide was presented during the course as 6 things to think about. Really, I'd say that the first 4 are considerations, and the last 2 are more about how you're going to implement these things. But the idea is that if you want to use machine learning technologies in mobile devices or at the edge, you have certain considerations that come into play far more seriously than they do when you're working on the cloud or even on your own workstation. You want models that are lightweight, they take up very little space, and they fit in memory in a very small amount of memory. You want low latency, so this involves both inference speed or training speed if you're doing it at the edge, although typically one does not. There's also improved power consumption here, and that can come not only from running these more lightweight models with fewer computations, but also in many cases you can do it without any networking at all. And the lack of networking can be a critical system design piece, especially if you have privacy considerations. One of the advantages of operating at the edge is that you can save the need to, you don't need to send your data to some cloud device that's going to be running the inference for you. You've got everything that you need right on your system, and you're not communicating any of your own data abroad, outside the system. So in order to do that, TensorFlow Lite really has a couple of different design considerations of its own. Namely, how do you make the model format as efficient as possible? There is a trade-off between efficiency of model and a couple of other things such as reliability or not reliability, readability, and maybe the flexibility of the model. And TensorFlow Lite definitely compromises on the latter two, readability and flexibility of its model files in order to maximize efficiency. And then you also have the heavy use of pre-trained models so that you can do as little of the work yourself. In many cases, you'll take a model off of the TensorFlow hub, which offers many models that have been pre-trained for you. You can fine-tune it or train it to your own data yourself. You may do that on the cloud. In some cases, you may wish to do that on the edge. But then typically what you'll do, if you've trained it on the cloud or a separate developer workstation, is then you'll put it into this efficient model format and port it over to your edge device, which only has to be able to gather the new data, such as through its phone camera, and then run the inference for you.
Robert, a question.
Sure.
So in terms of performance, like accuracy, for example, how much do you expect to sacrifice, performance in terms of, moving to TensorFlow Lite? Is that part of the equation? Is it part of the trade-off you're making? Because you didn't mention that.
You're right. I didn't mention it. It is mentioned in the course, and the suggestion is that in many cases, the drop in accuracy or inference performance is very small. However, it certainly exists, and it can be an important consideration, more important in some cases than others. However, they don't really go into it and quantify it in this course, but an important consideration for sure.
Thanks. Mm-hmm.
So in order to accomplish this, as we said, we use TensorFlow Lite, and the kind of 10,000 foot view of TensorFlow Lite is that you're really doing two processes. You're taking a model, maybe it's on the cloud, maybe it's something you trained yourself on a developer workstation, and in order to use TensorFlow Lite, the first thing you're going to end up doing is converting something that's not in TensorFlow Lite into TensorFlow Lite, and then you're going to use whatever you converted into TensorFlow Lite for the edge task that you want to accomplish. So in the usual activity then is you're going to train your model, maybe train it on the cloud, and at some point you're going to save a model, most likely, and then you're going to run the TensorFlow converter, and that's going to put it into this TensorFlow Lite, which is a very specific format describing your model very efficiently. And then on the other end, you're going to use it through the interpreter. So as part of the conversion process, not only are we getting it into a form efficient for reading by the interpreter, but we also, in many cases, want to further optimize it beyond the way in which it was implemented in our Jupyter notebook on our developer workstation. So these further optimizations, we'll go into those later in the course, but they can involve a handful of things. The one that we'll discuss in most detail is quantization. And on the back half of this equation, once we have a TensorFlow Lite model, we can pass it to our device. And then at the device end, what we really want is something that can execute very quickly, and we want it to have platform support across a very diverse platform support, right? We want it to be able to use the same format and run it on Android, iOS, embedded Linux, microcontrollers, and even be able to take advantage of accelerated inference. So we might be able to perform that final inference on CPU on the device, or using the GPU on the device, or even in some cases an edge TPU. So we're going to go into a little bit about the architecture and performance of the TensorFlow Lite ecosystem. And one thing that I want to mention is that this first week of the course, we're going to be focused almost entirely on the converter. And the last 3 weeks of the course will be more focused on the interpreter, because this first week we'll be talking more generally about the first half of the process, and the last 3 weeks are more about how do you take these TF-Lite models and deploy them in a variety of environments. So the converter is able to let's see, I don't think this is your converter here. This is a bit of a high-level view of the converter, but it's looking at, we have 3 types of objects that can be fed into the converter. You're either going to produce a saved model from your model in Python. In some cases, you can save it as a Keras model. Some of you may be familiar with this as an H5 format, whereas saved model is a TensorFlow format rather than the Keras format. And then there's another option here to save concrete functions, and they don't really go into this in the course. But what's happening here is that any of these 3 different object types, once they run through the conversion process and possibly get optimized, such as quantized there, you end up with this flat buffer object. And the flat buffer is this super efficient format for storing your TensorFlow Lite model object. And I think you can think of this as, this is where we're talking about that trade-off between efficiency of a model representation versus human readability or flexibility. You can imagine the kind of the opposite end of the spectrum. You could pass your model across as a JSON format, right? JSON's human readable as a dictionary. You could have your architecture clearly show your layers. You can show what the weights are in each layer, or you can attach another binary file that has the shard of the weights, such as we did with the JavaScript course last week. But in this case, you're not doing any of that. So the JSON is kind of the extreme flexibility, extreme human readability, not efficient side of the spectrum. And then TensorFlow saved model, this green object here, is sort of in between. It's got some readable aspects to it. I believe the Keras model certainly does. I don't recall for the saved model exactly. But then it also has weights sharded off, and there are some aspects that are made more efficient by that process. But when you're moving to the edge, you're really preferring efficiency over everything else. So this is an entirely binarized or binary file, and the schema is predefined, so there's no information about the schema in the file itself, and it is really just representing it can encode what the architecture of the file is, what the you can encode metadata in this file as well. There's two different versions, one with metadata and one without. And then it also includes all the weights right there in this flat buffer file. So very compact. And then you can send it to the interpreter. And one nice thing about the compact nature of this and predefined schema is that it's very minimal cost to then parse this thing and unpack the results. So really just efficiency on all ends, not worrying about other considerations, but that's the idea here. So
Robert, can I ask a question?
absolutely.
What would be the typical compression ratio going from saved model, for example, to flat buffer? Like generally, would you compress it like, I don't know, an order of magnitude or just twice or 20%, like roughly? Do they discuss that? I don't.
So they do not discuss that in the course. I'm just going off the top of my head on some. I believe some of the examples that we've seen where we looked at saved models and tf.lite models, you're looking at a factor of 2 or 3 sometimes in size. It's not the saved model already stores the weights fairly efficiently, and that's going to be the majority of most models. So short answer is I don't know. I don't think it's saving you orders of magnitude, but it is definitely speeding up the reading process, not having to interpret a schema on the fly.
Mm-hmm. Thanks.
Does anyone else know any more about that?
I don't really know for sure, but I mean, I imagine it probably depends a lot on how far you push the quantization, how far you put, like, you know, for example, if the saved model is everything is in, like, say, floating point format, right, which would be like 32-bit values, and if you quantize the weights to 8-bit values, for example, then right there it's like a 4-to-1 in terms of how large the weights are. And then if you do other things like pruning and stuff, it could get smaller. But, you know, maybe it depends on how far you push it, right? Are you pushing it to 16-bit, 8-bit? Are you even doing quantization at all? So I'd imagine it really depends. You know, it may depend on what kind of device you're trying to put it in. If you're trying to put in something really small, you might push the quantization really far. And if you're not, then you might not care as much. So I can't throw out any actual numbers, but just basically on how it kind of works, that seems like it could just vary a lot.
No, that makes a lot of sense. Great analysis. Thanks, Neil.
Hey, I got a quick question for you, Robert, while I got the mic here. When you go from the TensorFlow to the TensorFlow Lite and you end up with this flat buffer model, is that, I assume this is a one-way track, like you don't, like let's say you go through this process and then you later want to change something in your model. I assume you'd be changing it back in TensorFlow and then pushing it back. Like you wouldn't, there's no like reverse direction like from TensorFlow Lite back to TensorFlow, or is there? That's
I don't know the answer to that. I haven't seen, I haven't personally experienced a case where that would be useful because I've always got the original saved model or something already.
okay.
But I think you're
Yeah.
talking about a situation where somebody might have the flat buffer file, but not have the other stuff, right? And want to make some changes. I don't know.
Okay. That's probably the way you've drawn it. The arrows probably are one way, but it just was wondering.
Yeah, the flat buffer seems to be a precompiled binary file, like just a baked-in computational graph. Seems to be,
Okay.
for the TF
Okay.
Lite purposes. So if that's the case, I'm not 100% sure, but if that's the case, yeah, there's no way you go back, right?
Yeah, that would make sense.
Well, I think if you're using the version with metadata, I believe it has all the same information that the saved model has. I don't think it's lossy in that sense. So there could be an inverse function, one would think. Whether TensorFlow has provided that, I don't know.
Okay.
But I think the saved model automatically encodes some metadata, and depending on what parameters you set for your flat buffer file, you may choose to eliminate the metadata. So you may not have things such as what the names of your labels are for your classes.
Right. Yeah, you'd probably lose some of the information that was used to create it.
Yeah.
Okay.
So as I mentioned earlier, the vast majority of this first week of the course is going to be on the converter, but there is a little bit on the back and the interpreter end of things, and that's right here. And there's a little bit that there's one section where they talk about delegates in TensorFlow and TensorFlow Lite, and the idea is that you can basically, as it says here, enable hardware acceleration of your models by choosing to use an on-device accelerator such as a GPU rather than the CPU on your target device. And there's a handful of issues that can happen with that. The one thing that it can do is it can eliminate some unnecessary operations in the conversion process there. But there is a downside in that it is possible that there are TensorFlow operations that are not actually included as part of the delegate as part of the graph. So it's possible that you'll get some cases where it says, well, I can move 80% of this model to the GPU, but I have to do this step on the CPU. And then it decides, I think it does optimize within there, but at that point, you may end up actually losing out if your latency and communication between CPU and GPU overcomes the advantage of processing part of your model on GPU. So I think he indicated that there are some tools for investigating that. There are actually some benchmarking tools that we don't really go into, didn't talk about in the course at all, but I thought this was particularly interesting here. A whole sub-library here with benchmarking tools to measure things like inference time, memory usage. There's an Android version and I think an iOS version at the bottom of this page as well. So, but these are considerations that if you're going to use GPU delegates, you may want to just test things on your system, try a couple different things before actually moving anything to production.
Robert, I see there's a mention of, maybe we'll get into this when we talk about the, later on when we talk about the interpreter, but I see there's a mention of a TensorFlow Lite runtime. So is that part of TensorFlow Lite like there's something called a runtime that actually executes the, are these benchmarking things kind of built into the runtime?
Did you see that in the middle of the page? I don't see that.
Scroll down a little. Oh wait, where was it? Keep going, maybe. I saw it. There was like a paragraph. It was at the bottom of the paragraph. No, I don't know what happened to it. Can you search for runtime? That's all right. Oh yeah, there it is.
Available options and output formats are slightly different.
Oh.
I guess that's just talking about
Maybe they each have their own run. Never mind. Forget it. I thought I saw something about a TensorFlow like runtime, but
yeah, I think they're just talking about different edge.
Okay, got it. Thanks.
Mm-hmm.
And I have some numbers for you, Dimitri, who asked about numbers. So Robert, you're going to cover this as well in one of your notebooks, but just looking at the base model, like a MobileNet V2, it's about 8 megabytes in size. The saved model is a little bit bigger, 8.6 megabytes. And once you convert it to TF Lite, it's about 2.8 megabytes. So it's about 3 times smaller in size. This is just a very basic MobileNet-based image classifier.
Yeah, interesting.
And that's the one that was trained on cats and dogs that we're talking about.
Yeah.
So yeah, that's one example. I'm sure with different options, you can vary that quite a bit.
And David posted a link with more performance-based metrics. Sorry, Robert.
Oh, cool. Let's see, I think we've covered as much as we're going to cover on the GPU and delegates, and I think the rest of this week is entirely on the converter process. This is actually the library as part of TensorFlow with a pretty long README page here on benchmarking, and I think they have an Android and iOS section. Or no, I think this page only has Android, and somewhere down within this GitHub library, I think there's an iOS folder here that has a similar framework for it. So, as mentioned, this first week we're talking mostly about the process of going from your Python environment to, and the end goal is to get a TF Lite format model after conversion. And there are a number of optimizations that one can do. And they describe really 3 types of optimizations in the course. Quantization is a really important one. Another one the other ones are just mentioned and not described at all. But the second one is weight pruning, as Neil was mentioning earlier. And what weight pruning is you're basically looking at your model after training, and you're trying to find out which weights might not be too useful, right? If you have weights that are really close to 0, maybe they're not doing much, so you can save space in your model without really losing much performance by just chopping those off entirely. That's as an example. And the other types of optimizations that they talk about are what they call topological optimizations, which really are about changing the structure of your network in greater ways than just chopping off a few weights. The 2 they mention are tensor decomposition and distillation. And distillation is this process where you'll train a teacher model, kind of a large teacher model that is doing the classification for you, and then you're going to use its predictions to train much lighter weight student models, and you're going to use it as if it's a regression model. You're going to try to get the students to predict the teacher's predictions, the the predictions, not the classes themselves. And the idea there is that in many cases, by training in this fashion, you can get a very, very small model to learn a model that is just as accurate, or a model that is much more accurate than such a size model would be had you trained it itself. By doing that, you're learning kind of which ones the teacher is most confident in, so you're learning more about what to look for. So optimization, yeah, this whole page talks about those ideas. I'll skip quantization for now because there's a bigger section on it later. Lawrence does mention in the course that he finds there's a command line interface for inspecting saved models. This is assuming you've finished training your model and you haven't yet converted it, but you want to know a little bit about it. You can load it and just look at it on the command line, and you can quickly get information about what does the input format look like, batch, horizontal, vertical, number of channels, and what does the output format look like, batch size, number of classes. So this is a ImageNet model trained on 1,000 classes. Useful tool. So I'm going to go over to maybe reconnect here and start running this in the background just from scratch again. So the little bit about quantization here. There are a number of different options for quantization I'll make this full screen, I guess. Number of different options for types of quantization that you can do before conversion, as part of the conversion process to TensorFlow Lite. And this little graphic here illustrates many of those decisions. So you have post-training quantization, and this is, you're really at that point, you're just making the weights a little smaller. So maybe instead of floating point weights, you'll have 8-bit integer weights, but you're not touching the activations, and you're not really limiting the computations themselves on the other end. You're still doing floating point computations at the edge device. You are just using a smaller model coming in to do that with. For this, you actually have a number of different options here as they show. You can optimize this for size, for latency, or both. And the both, I think, is just a trade-off between size and latency, where size is the memory footprints of the model and latency is the speed at which it's executing. And we'll see some code in that notebook that I just started, which shows exactly how to do that. And then if you have what they call a representative data set, which is if you have some data that you want to see how, if you have some data that you want to use for post-training integer quantization, what you're doing there is you're quantizing the activations as well as the weights. So at that point, you want to look at some images coming in, kind of figure out what the dynamic range of your activations might lie over, and then you can choose your, how to map your floating point original weights in the Python model to integers for quantization purposes, such that you'll take full advantage of that dynamic range that's available, or maximal advantage anyway. If you don't have a representative data set, the model will always just fall back to using quantized weights only, but otherwise you can get quantized activations as well. Then you have a further option that you can do which limits it to int8 ops only. And again, if you can't accomplish that, then there is a fallback mechanism. Although I was a little bit unclear in the course materials, it sounded like if you called this, it would possibly just raise errors, and so then when it raises an error, you would have to go back and do this manually. I don't think that happens automatically, that you would change it to just falling back to post-training integer quantization without int8 ops. There is another whole section here about tf select, and tf select is basically another way of that they've recognized that not all TensorFlow models are convertible into TensorFlow Lite, even for those operations which are supported. And by the way, the TensorFlow Lite guide does have a page somewhere in there. I think it's TensorFlow Lite /ops/compatibility or something. There's a link in here somewhere. And it will list exactly which operations, which types of layers, which mathematical operations, everything that TensorFlow Lite can do. So you can see in advance where you might have a stumbling block with your own model. Look like it's pretty comprehensive for inference types of operations for convolutional models. I think they have some support for basic recurrent nets, but none for LSTMs and no attention or anything like that. So really, I think the main use case that they're serving right now is the image-based models, which is probably why we have a course full of that.
What about voice recognition, Robert? Did they discuss that?
Not that I've seen. Has anyone done voice recognition with TensorFlow?
No, I just thought, it would be logical to push some of that functionality on Edge too, right?
Absolutely. I have played with the speech recognition API from Google, and there's many obvious applications you can think of where that kind of thing would be especially valuable on Edge, especially in translation apps. And, but I don't think there are any such examples in this course.
I don't know. Yeah, maybe you can do one coding exercise at the very end, if there's none. I'm sure it'll have its own fun and challenges.
Yeah, something like that. So let's see, what else do we need to accomplish here? I think I have another notebook over here that I'll run. Actually, I don't need to. So just wanted to step down through the example notebooks. Actually, there's two of them. Let me stop my share briefly and share the entire desktop. So I think I have the other one in Safari. So they give the hello world of TensorFlow models for TensorFlow Lite now. And of course, this is our favorite line here. Our favorite line because it's the exact same data that we've seen before, minus the one deviation we had one week.
Straight perfect line.
Straight perfect line, absolutely. All odd numbers in the y. So, and this is just provided as an example, very quick way to get a model trained and saved. And we saw, I think we saw in course 1 where you do the TensorFlow saved model format, and you're converting it. You use this from saved model here. There's actually, as we showed in one of the slides earlier, there's 3 formats that you can go from saved model, from Keras model, or from concrete functions. They're recommending the saved model, but I think that's, the TensorFlow format. Why not? So once you've converted your model, you'll typically write it to, in this case, you're not doing any optimization, just converter. But the command here is simply tf.lite converter from save model, and then converter.convert. It's pretty easy once you set it all up. In the next notebook, we'll see how you can throw some optimizations onto that converter as well. And then, oh, this is pretty cool. The TF Lite Interpreter, you can actually, we mentioned that you want to run the interpreter on the edge device, but TensorFlow also provides a way to interface with that interpreter through your developer workstation as well. So you can call the interpreter right here in Python and get a sense of what it's going to do on your edge device. So in this case, it's just going to allocate tensors, and then it's going to get input details, output details of the model, and then here there's this whole process where you set the tensor, you run .invoke, which actually runs the model, and get the output details. And then here, this example was just visualizing the result, which is actually a line. Who knew? So we'll return to the other window to look at
Before you go, Robert, actually, if you go to your file settings, so I noticed the size of your TF Lite model was 780 something bytes. When you
file settings, where's that?
Yeah, so if you scroll down a little bit, when you call the converter, so yeah, it says converter, converter.convert, 700, line 6, 768 bytes. When you wrote it to your disk. And then if you go to Jupyter Notebook, all the way up in the left corner, it says File, Open. So I don't know when you ran this, but saved model, if you click on that one, you might have to zip it all together. I don't think you can tell, but yeah, this is the structure of the saved model.
I see.
I think it's in assets.
39 kilobytes there. Assets is empty. I think that's where you're.
Yeah, go back. It should be that saved model of PB then, 39.
Yeah, must be.
Kilobyte. Is there anything on the variables? Oh, there's a few kilobytes there. So
that must have stored there as well.
So let's say 40 kilobytes, right? So 40 kilobytes, 40,000 bytes, and you went down to 800. So 40,000 divided by 800. 50x reduction. I mean, that was just a single neuron.
Was there any quantization involved in this notebook? No.
And keep in mind, this one wouldn't actually matter there because the single weight and bias are a really small fraction of this TF Lite file. I think this is an extreme case. You will never see another model with such a small fraction of it being encapsulated by the line.
It may just be this one is so small that like there's a lot of overhead in the TensorFlow file that's not in the TensorFlow Lite file, so it's just dominating.
So this could be a bounding case, right? You'll never do better than
50x.
what 60x, 50x improvement or something.
We know now.
But again, that's without quantization, and so who knows?
Sure. Yeah. You're right. Yeah. Could be.
But I think Neil's right there. It's really just the
Well, I'm just guessing, but
so little of it's in the weights that it's just almost entirely overhead.
It's just two numbers, right? Yeah.
Cool. So we'll move over here to this cats and dogs example, which goes into a much more comprehensive detail of what exactly we've accomplished through this first week of the course. So here we have TensorFlow version 2.x, import a few things. We're importing from the hub, we're importing from TensorFlow datasets, and we're using TensorFlow version 2.4.1. We're on Colab, and we're on a GPU device. And now we can select the hub module to use. Oh, by the way, I should mention that regardless of whether you're taking the course, this is one of the files that you can find right on that public GitHub site, the Lawrence's GitHub site that was shown earlier. So you can certainly run right through this yourself as well if you want to play with it. So you have the option here of a MobileNet, and I think Inception was the other one. Yeah, Inception v3. MobileNet v2 we'll stick with. Some pre-processing here. One thing that's a little bit important, you'll encounter an error if you run the file as originally written. And that's because instead of this line that I'm showing right here, there used to be another line. I think we can show it over here. Actually, no, it doesn't. It used to use an old method here, subsplit, which is now deprecated and throws an error. So you need to replace those first two commands in that cell, which were there, with the one that I have put in there and that we were just looking at. So, by the way, just a note here that our community here, as we're going through this course, we are compiling a small list of errata and any things that we want to bring to the course developers' attention. We're hoping to get an audience with Lawrence and soak up some more wisdom from him in another happy hour at the end of this adventure.
Yes.
So at the time we'll also provide them with our list of observations of things that could be updated, since this has been a year since a lot of this course has been written now. So if you notice anything in your own journey through this, that's the GitHub right here. El Moroni DLA course, course 2, TensorFlow Lite, week 1. So anyway, we've fixed that error now. You don't need to fix it if you're running TensorFlow 2.2 or earlier, I think. I don't remember. And then you get splits. You get train examples, validation examples, test examples. These are different data sets. The number of examples here is roughly a couple thousand, I think. We're going to define a method to resize, just do some pre-processing on the image, resize it to the MobileNet, and normalize it, divide by 255. We'll set batch size to 32. Here, just some pre-processing, but good things to know. We are shuffling the training examples. We are then mapping that data set through the format image command that we just defined. We are batching it. And then one thing that's kind of useful is that almost all data set fetching commands in TensorFlow, you'll want to put this .prefetch 1 on the end. That really just helps you prefetch one element from the batch while you might be working on getting, or you can process one that you've fetched already while you're fetching the next one. So it's a little bit more efficient to write your code in this way. That was new to me recently, so I thought it was worth mentioning. Validation example is something similar, just no need to shuffle them. And the test example is kind of important that we have to give this a batch size of 1, so we can get one at a time. So inspect the batch, and it all looks good. Size 32 by 224, 224, 3. Define the model. Here we have the option of doing fine-tuning or not. Feature extractor, this is really just, we're going to treat MobileNet as a black box. So input and output, and feature extractor is our MobileNet. So all we're going to do is drop a dense layer on the top with our number of classes, which in this case is 2 for cats and dogs. And
Robert, do you mind expanding that fine-tuning, because there's actually code behind it? Click on that play button.
sure.
Yeah, just for there. There you go. Perfect. Thank you.
Yeah, this is also new to me. I don't think before this course I had seen these kinds of checkboxes here in
Yeah.
Jupyter.
That was new to me too. That parameter, that add param, was new to me as well.
Yeah, this looks like a comment, but it's actually code here after.
Yeah, it's code for that widget on the right of Colab.
Mm-hmm. So, okay, dense layer here. Activation softmax. Usually for a binary problem, you'd just use a sigmoid, but I guess this makes you a little bit more extensible to multi-classes. A little loop or condition here allows you to, if you've chosen fine-tuning, then you can choose some of these other layers here. Again, we see this slider, same kind of idea. You can define a slider with a minimum and maximum and step that way. And you can see that if I change, like I can just edit this right here to 10 or something, and it immediately adjusts the slider. So then, train the model, compile it, SGD, learning rate, 0.002, momentum, sparse categorical cross entropy, just 5 epochs. It's got really good accuracy, even in the validation set, it's almost 99%. Cats versus dogs, saved model. This is that command line interface that we were talking about earlier that Lawrence advocated for using, where you can see the inputs and outputs after you've already got a saved model on your disk. Just run it right on the command line. Now that we have a saved model, we can start the conversion process. So we first of all define converter equals tf.lite.converter from the saved model. And now we can do some quantization. And in this example, we'll do 3 different things here. So first of all, we're going to choose the optimize default. We could, in this case, we could have chosen optimize for latency or optimize for size, as we mentioned earlier, depending on which of those two we're most interested in. And then in addition to quantizing the weight, which this is doing, we'll do post-training integer quantization for the activations as well by making sure the all model math is quantized. So we'll measure the dynamic range of activations by throwing in a representative data set. And you actually attach that to your converter. And that becomes generator here. And then they're going to try full integer quantization as well. So now you're only going to be able to output integers from the operation. And then you do this tf.lite.offset and built-ins int8. So, and then in the course, they talked about using tf-select to possibly amend that as well with you can choose tf-lite built-ins or select offset to select tf-ops if you want a to play with the set of operations that's available to you a little bit more.
Robert, just to clarify, this representative data set is completely different of any other optimization technique like full integer optimization, right? You can do either or both, correct?
Can you repeat that? I think the answer is yes, but
Is this full integer quantization completely independent of that representative data set? To me, that's when you expose your model to different numbers, to different inputs. You look at the output or activation ranges, and maybe you look at, you know, like 8-bit or 4-bit. I don't know what other options you have for integers, but
so my understanding here was that you almost always, I can't think of a good reason why you wouldn't, or put it this way, if you don't have a representative data set, then you probably don't want to make your activations integers because you won't know how to scale them. And
Right.
floats can vary over many, many orders of magnitude without really compromising accuracy. So I think that's why we're doing the representative data set here, is just to get a sense of what the range of activations our model will get on data that we feed into it so that it knows how best to quantize.
In my understanding, the representative data set is basically giving you a min and a max. You're still using floats in between when possible, but it's telling you that the minimum is 0 and the maximum is 100. So maybe you only need, you know, 7 bits, 128, 2 to the 7, versus minimum is 0 and maximum is, you know, a billion. You need like 15 or I don't know, 20 bits. Now the full integer one, I'm not sure how if it's how it makes a decision, because you're right, like one number to the other, one integer to the other is a huge weight or huge bias in your network, right? We've seen like even small tweaks can take your network to a weird state. So I don't know how it makes the decision to just use integers.
Well, I think what you're looking at here is it doesn't really matter what the original dynamic range of activations was. You just want to know what it was so that you know what to divide out, right? If you had a dynamic range that went up to 100, but you quantized it as if it went up to 1,000,000, then you're just going to peg everything to the same value and you'll ruin your network.
Got it.
So I think it's just about figuring out kind of what to divide by.
The binning process, right?
Yeah.
Okay.
So what exactly again is the difference between the post-training integer quantization and the full integer quantization? Is it just the inputs and outputs? Like it looks like for the post-training integer quantization, the resulting model will be fully quantized, but can still take float input and output for convenience. Is that the only difference? It's just that the inputs and outputs are float, whereas in the full integer quantization, even everything is integers in that case. Does that make sense?
So this one says the input and output can be float. The other one says the output is specifically integer. Right, that's one difference I see immediately.
Okay.
Yeah, it's a good question. It does look like post-training integer quantization is trying to be flexible so that it can still work with floats.
Yeah.
The latter one is kind of forcing you to use integers. I think that's why they said it would give you an error if it couldn't.
Yeah, it looks like now I'm reading there's a sentence opposite do not have quantized implementations will be automatically left in floating point. This allows conversion to occur smoothly, but may restrict deployment to accelerators that support float. So I guess the post-training integer quantization tries to make everything except maybe the inputs and outputs integers, but wherever it can, it still leaves them as float. And it requires a processor that supports float, whereas the full integer quantization, absolutely everything is integers and the processor need not support float. Is that does that make sense?
That makes sense, and I think you're understanding it. Sounds basically where I am.
One thing I'll add to that might help with George's question is, at least what I've seen is a lot of times with the full, like when you have networks that are quantized, where with both the weights and the activations are quantized, often there's like a scaling, like the ranges are determined at each layer in the network. So right, you go through, and you know the weights and the activations are multiplied together in the matrix multiplication. You go through the activation function, and the output of the activation function is often scaled or at that point. So to get it back into a good range. So basically you want the sort of the dynamic range to be good at every layer in the network. So to make that happen, so you don't have vanishing, you know, values through the network due to the quantizations. Often, I don't know how that's done here in TensorFlow Lite, but you know, especially if it's only 8-bit, if everything is only 8 bits, then you know, you get to the output of the activation, and if things are really, if the range becomes compressed, you want to like expand it back out again with some kind of scaling. So that's usually what I've seen.
Yeah, that makes sense.
I don't know if they're doing that here. I bet they are. Anyway.
Yeah, that's a good point. Thanks. So, let's see. So I think you know there's obviously a lot about quantization that been we've been shown a lot about quantization. Some of it's still a little bit confusing, but at the end of the day, we're then just using that to determine how exactly we're going to convert this Python model into a TF Lite format. And then the actual conversion process is pretty trivial. It's right here on this line. And then we get to use the Python interpreter so we can inspect how our model is doing on the developer workstation. So we do a tf.lite.interpreter, we allocate tensors, and then we can get some predictions. And we're going to look at, I guess, 10 images here and the predictions for each of them. And I printed out the predictions just to get a sense of what we're looking at here. Now, one thing to note is that since it's been quantized, it turns out that in some cases they don't actually add up to 1 exactly anymore. I guess this 0 plus this 0.996, but this is the prediction for a cat on the left, I think, and a dog on the right if it's 1. So then there's a utility function for plotting. You can kind of see, okay, move this bar here, and we get different, why are we seeing the same image each time? Maybe I decoupled it from...
No, you can just change that index. Should update.
Yeah, I was playing with this code earlier in another collab, so I'm not sure. Usually...
Hit the play button. Does it?
Is that... Okay, there we go. So I think the only one that it was somewhat not confident in was this one. Dog 79%, maybe it's the pointy ears. So I actually had taken this apart a little bit further and modified this notebook a bit here to try to look at comparing these different sorts of quantizations, and basically looped over this with 4 different versions of the converter. This is not in the original notebook. I just tried to expand it to do that. and really didn't learn as much as I was hoping to learn by doing that. One thing I did note is that the probabilities don't really change too much from one to the other. So to clarify, I guess I'm doing one converter with just optimized at default, so I guess full or no post-training quantization. And then here's one that's converter 0. Converter 1 and subsequent will all be optimized for latency, and then number 2 will also be post-training integer quantized, and then number 3 will get the full integer quantization.
Cool.
And I was just curious to see if it was going to affect the accuracy of the predictions or the confidence levels, and if it was going to affect the runtime, at least right here within the Python environment. And really got not much to look at here. I didn't plot it, but doesn't seem like it changes too much. You can see which ones are integer quantized and which ones aren't, but the actual probabilities don't really seem to be altering too much from one to the other. You'll note that I think everything here in this batch is pretty confident. Here's one that isn't. It's this example number 1 again, where it actually did move from 90% confidence of a dog, and then the more quantized it got, it became only 70% confident.
Interesting.
But I think this is just one single example, and I hesitate to call that the rule. I didn't really notice a significant difference in runtime in the Python environment. In order to investigate this really, though, I think you'd want to put it on a device and benchmark it in the way that we referred to earlier, but I haven't gotten too deep into that.
Did you show runtime as well, and it was about the same?
Did I show runtime? At some point in this notebook, there we go.
Oh, there you go. 23, 22, 24.
This is to do 32 images, I think. To do 32 images total took 23 seconds, 22 seconds, 24, and for the 4 different versions of quantization. But I don't know. I just really did this the old-fashioned way by throwing a time.time loop in there.
Perfect.
So yeah, I'd be curious to learn better about how to benchmark these things. But that's I think that we've essentially reached the end of week 1. It's been a lot of stuff this week. I hope that sets us in place for subsequent weeks, and we'll see. I know George has a lot of material here, so I don't know if we'll get through it all.
We'll try. Awesome. Thank you, Robert. I appreciate it. This was awesome. Thank you for taking a deep dive into what goes behind the scenes when you use TF Lite. I mean, week 1 took a while to wrap my head around it, so it was a lot of content. So thank you. Cool. So friends, get ready for some more code and some more cool applications we're gonna look at together. Before I do so, there's some resources that are mentioned in the course. There's a training course for free for Android basics in Kotlin or in Java. You can learn both. We're going to use Android Studio for this week. We're going to deploy our models both on an emulator as well as on our phones on an Android device, which I have here, Pixel 4a. The emulator is pretty cool. It has some nice features. You can actually look at the layout of an app as you're coding it. It has a nice emulator as well, which I really like. It has like this VR setup where you have like a living room and some objects in it. We're going to look at it. We can expose that to our model as well when we do image classification or object detection. Some really nice features. In some other setups, we also use it to measure how much RAM, CPU, network activity, or power consumption our app is using. So it has a lot of profiler-based features, CPU, memory, network, power as well. And I'll mention this in the end as well, but Google I/O is Google's largest conference. It's going on live this week. They also have some new interesting features related to Android and machine learning. I'll mention that at the end as well.
George, that profiler example that you showed there, that's app specific or for the device as a whole?
This is device as a whole. Yeah. So if you connect your device to it, it reads CPU, memory, network, and power consumption. Yeah. We've seen this in other events, in our AI visual meetup. So yeah, network, energy, memory, CPU. Cool. So week 2 really covers the flow that Robert followed, where you have a model in TF Lite, you capture somehow an image either from your local file or from your webcam. You need to do some kind of pre-processing because the size and also the color channels used by a model, by your device is usually different than what the model expects. For example, we're going to be using MobileNet, which expects 224 by 224 with height by 3 color channels, but my phone's camera uses completely different width and height and completely different color channels. So there's a pre-processing step for us. And then once we bring it down to the necessary input format that our model expects, we can call our model, our TF Lite model, and then we have to interpret the results, and somehow we have to notify the user back using the UI of the app of this is a cat, this is a dog, or this is an object from the ImageNet data set, and this is the confidence level and so forth. So that's, I also have this slide here. And if you want to take a little bit of deeper dive here, this generic 4-step process that Lawrence mentioned in the course is really a really good benchmark for us. So we're going to initialize the interpreter. This is step number 1, and we're going to connect to the interpreter that is using our model. We're going to prepare the image input, as I mentioned. Different devices use different sizes and different color channels. We're going to actually call our model, perform inference, and then we're going to take the results and somehow show them back to the user. To give an example of what kind of processing we're talking about here, this is an example of an image. If you want to zoom in at 1 pixel, a lot of devices use this RGBA value for coloring, for formatting color, as well as I forgot what A stands for. Have it here.
Alpha.
Alpha. Right. Alpha. Indicates how opaque each pixel is. So we want to convert that to an RGB value. Not only that, but we also want to normalize it because our model expects normalized values as inputs. Cool. So with that said, I'll talk a little bit about Android Studio. So I have it open here. I'm going to look at 3 examples real quick. The very first one is the model that Robert mentioned in the beginning, where it used a backbone of MobileNet, I think, yeah, as well as our own 2-node last layer using softmax to classify images of cats and dogs. And I can always zoom in here more, so please let me know if what I'm showing is not legible. So the layout, a little bit, just to show you the layout. In Android Studio, you can import your project, but really the layout is cat versus dog, and then I'm looking under app, under source, main, assets. Under assets is where usually we keep anything that we import from our development environment. So
can you zoom in on the left a little bit?
it's a good. question. I can make it bigger, but there's a shortcut that I don't always remember for Mac on how to zoom in.
I mean, it's fine. It's a little bit tough to read, but it's legible.
Yeah. Yeah.
Don't worry
I'll
about it.
figure out for next time. I'm sorry. Yeah. So under assets, we have our TF Lite model, which we can inspect or we can reveal in Finder. Oh, sorry. Maybe this is a better way to look at it. I don't know. So cats versus dog, app, source, main, assets, Java. Sorry, assets, and then under Java, usually you're going to have your code. Here you're going to have resources. So and so forth. So yeah, that's our two labels one, our two label category classifier. The basic app is under source main, this build.gradle right here. And this is where you basically have to, like we have imports in, make this bigger, in Python. This is where you have your imports version in Android, right, in Kotlin. So you need some basic, obviously, Android libraries, Kotlin libraries. We're going to define our own application here. I'm going to give it a name, TF Lite cat versus dogs. And down here under dependencies, this is very important. We have to specify that we need to run TF Lite, TensorFlow Lite. I think that's the only, or that's the main dependency that we need to do the inference. And another very important thing is we have to specifically tell Android Studio not to compress our model.tf Lite. Otherwise, by default, it might try to optimize it for storage, and it will actually try to compress our model, in which case we cannot use it because we cannot read from it. So those are the main things that we have to do at this build.gradle. I'll show you under resources, images. These are some images of cats and dogs. So we get a few more. But we'll run some inference on these images for us. And these are hard-coded images under resources for this very basic example. Under this resources drawable, sorry, it's not under resources, it's under resources layout. I was looking at the wrong folder. So under layout is an XML file. Android Studio is showing it to us as an UI, but it's an XML file where we hard code. We have a layout of 3x2 grid here where we actually overlaying the images. So these are the images from the resource folder. We're just placing them in this grid of a 3x2 so that when we open the app, we're going to look at this grid of 3x2. And let's look at the actual code that does the actual work under Java, under COM, under TF Lite. We have a TF Lite and a view. Let's look under view, this image classifier.activity. This is the main one, or one of the main ones that sys the UI. We'll import our package as before, some other imports that we don't have to get into details, but basically we want to read things from the camera. That's what this bitmap is. We want to view things on our app. We want to display text on the app. This is the library called Toast in Android. And obviously we need our TF Lite classifier as well. And the way this is structured is we're going to have an input size of 224 by 224 by 3. We're going to use our model path, which is converted model.tf Lite, and our labels.txt. we will initialize our view where we're going to lay out this 3x2 grid. That's why you see 6 elements here. And really the basic thing of what the app will do is it will read the grid. It will actually try to detect where the user clicked. This is done by this command here. It will pick up that space where the user clicked. It will identify which image that belongs to. It will pick that image and it will run it through this classifier. It will return the result of other cats or dogs, and then it will basically print it out. That's why this toast make text is here. It will print out the title of our finding, and it will print out the one with the highest probability. So it will be sorted by confidence level, and in this case, we're just printing one value. So it will be either cat or dog. So let's look at this classifier a little bit deeper. What does it do? We're importing it here, tf.js classifier. This one has a little bit more code as expected, but just to give you an idea of what we're looking at is we have our input size, which is coming as an argument, is 224. The channel size, which is 3. Some standardization. Remember that the pre-processing that we have to do, we have to subtract 0 and divide by 255. In this case, we're making everything from 0 to 1. And we're going to return just the top 3 results. And we're only going to return results that our classifier detects more than 0.4 out of 1. So some options that Robert, you mentioned in the beginning are some interpreter options. And specifically here for Android, you can set how many threads you can run in parallel when you do this. As well as for Android, if your device supports what is called a neural network API, it's basically an accelerator. We want to use that as well. Then we want to load our model from our model path with the different options, as well as our label list. Lawrence goes into more details. I'm not going to cover this too much, but basically, this is a way for us to read the model as a file byte by byte, and you have to set up all this input stream and file descriptors just to basically read your load your model from memory into execution, as well as the list. Then the process of converting or reading the or doing actual inference is we take our image, make sure it's of the right format, 224 by 224. We convert it to that 0 to 1 threshold that we saw before. Then we call the interpreter, and we store the results in this result variable. We also want to sort them by confidence level. This is some code here that does that RGBA to RGB conversion. That's why you see the shifts here, as well as dividing or removing the mean, which is 0, and dividing by 255. And the get sorted results uses this priority queue in Android, which is basically a smart way for us to keep our results sorted as they are entered in the queue. So it's a sorted queue, basically. And in the end, we're going to return max results, which is 3, but only those that are above that threshold of 0.4. So this is the nuances, basically, of working in Kotlin and Android. I found this a little bit, code heavy, but it's part of the app development cycle. Awesome. Before I show you the app, the next thing we have to do is we have to build this app. So under make, build, make project, or make module cat versus dogs. Once you do that, when you go under run sorry, is it run window tools? I think it's under tools. Yeah, edit run debug configuration. Then you can create what is called, create a new one for us, an Android app. And I can specify the module I just created. So I have it here for us. It's just pointing to that model that I was just built and compiled. Then the next thing is you have to create you have to use either a virtual device or a real device. And to do that, I had a hard time actually finding this menu on this app. You need to use this AVD manager. I couldn't find it easily, so for me, I Googled it, and there's, yeah, this is the syncing. There was a shortcut for me that I remember I used to find it. I think it was Shift A or something like that. Yeah. So once I was able to find it, I'll create one new for us, create a virtual device just to see how it is. So you can create a TV virtual device, a phone virtual device. This is all on Android, right? So Wear OS, if you want to have a smartwatch, tablet, Nexus 7, or for car. I did phone, I think I did a 5.7 inch. Next.
Okay, did you car to identify what unfortunate animal you just struck?
Yeah, or maybe it hits the brakes for you.
Yeah, that would be great. Yeah, it could automatically avoid it.
Right. That's part of the self-driving car that we're building in the end in Raspberry Pi. So next, you might have to download the different versions of Android, in this case R, API level 30. I had to download that. It was about 1 gig in size. Next, give it a name, and then finish, and that will create your virtual device, which I also have here. When you click on it, sorry, I don't want to run this. This is the last one. When you click on it, it'll pop up a new emulator for us. So let's do that right now. I can also, so that was my Pixel 4. But also when I connect my phone, you'll see another option for me that says Pixel 4a. For now, I'm just going to run this app on my so it's actually compiling it. It's deploying it on this emulator, and this is a full-size emulator. You can see here different apps, and once it's done deploying, it will open up this cat versus dog app for us. So that's the layout that I was explaining before, this 3x2 grid, and you can click somewhere, and it will give you the label for that image. Dog, cat, dog, cat, dog, cat. And what Lawrence did, which I find interesting, I'm going to close it. But the interesting part here is you can actually set, for example, here, a debug a checkpoint, so that when we run this example, we want to see exactly the flow of the code and also what results are returned. So let me do that, and let me run, instead of play here, run app, I'm going to do debug app in Android Studio, and the emulator for me, and it will now run it in debug mode. I'm going to move it a little bit to the left so that you can see the code.
Is that available only when you're using an emulator, or does it work with a real device too?
I didn't try it with a real device, but I'm pretty sure the real device would have to be connected somehow. I think you can also do it with a real device. I haven't tried it though. That's a good question. So I have only one checkpoint here. I'll click somewhere, and my emulator will run all the code for me, and it will stop under results. And under here, results is what I have what my model returned. It's a list. The first item is 0.008 and the next item is 0.99. So I'll do next. Yep, that's what we called our classifier. And this is where we are about to print the output on the UI. And let's see how that looks. It's a text that says title equals dog, confidence is 0.99. So if I do it next, you'll actually call multiple other classes to render this. So I'm not going to go next, but at the end of the day, we'll plot here that class for us. Awesome. I wanted to show you as well how this looks on my phone. And I also want to show you what settings you have to do on your phone as well. So I'll join the meeting on my phone as well, and I'll share my screen for you guys. And I'll mute myself. Perfect. So let me share my screen. Oh, sorry, I have to stop sharing. So you see my app, dog. There's a slight bug in my app. I don't know why, but all my images are classified as dog, and I haven't figured this out yet. But the other thing I wanted to tell you is this setting you have to, where is it? Under settings in Android, if you go to system, before you do this, before you connect to Android Studio, under advanced, there's a developer options. If it's not there for you, you might have to, I think, select this multiple times, like 7 times or something like that, if it's not enabled. Once it's enabled, you want to turn it on, and you want to have this USB debugging on. That's the only setting you have to do. Cool. I'll stop sharing here. Awesome. So that was the first one. Let me quickly show you 2 more, which I really enjoyed. Let me close this. Another one that was really interesting was using a pre-trained model on MobileNet. And under app, source, main assets, you can see the labels here. Let me zoom in a little bit. And MobileNet was trained on ImageNet, right? So we can actually see the classes of ImageNet: background, tench, goldfish, and terrapin, beagle, old English sheepdog, very specific, Eskimo dog, cats, hamsters. But what we're looking for, so let's make sure there's 1,000 categories. We have a guinea pig, which is very exciting. All right, so you know where this is going. Let's look at our build Gradle. Again, TensorFlow Lite is what we have to import. And then the classifier does, let me make this smaller. If I remember correctly, so yeah, this is where we set up again the options. We load our model, read from the camera in this case, and we convert it to whatever our model expects. and we run the interpreter. I think the conversion here was, no, it was okay. It wasn't that complicated. And the sorted results is exactly the same as before. It's just that now that reading from the camera is way more involved, because we're not reading now static images from the assets folder. We're actually reading from the webcam, either of the emulator or our phone, as you'll see. Trying to remember here. Yeah, we return only one result here. This result.get 0. We're only returning the one that has the highest confidence. Cool. So let's run this on the emulator real quick, and I'll run it as a normal app without debugging it, and I'll also run it on debug mode so you can see what is it returning. Let me put a checkpoint for us. Yep, I have one here. Perfect. Welcome, friends. This is a follow-up of our deep learning adventure from last night. As you notice, this is just me and Robert tonight. We had a little bit of a glitch last night. My computer froze with multiple instances of Android Studio opened up, as well as me trying to run the debugger and recording at the same time over Zoom and joining from my phone and running detection and so forth. So it was a technically interesting evening. So we're gonna do a redo. Basically, we're going to do another session with you, friends. So you're in for an exclusive tour with Robert and I and deep learning adventures here of some image classification and object detection tasks. Robert, welcome.
Welcome, George. To be clear, the tour will be almost exclusively led by George.
It's led by both of us. We needed 2 tour guides for this. Awesome. Friends, thanks again for joining us online on YouTube and other social media channels. We love and appreciate you and can't wait to see you live or over any other events that we do in the future. So let me share my screen real quick here. And where we left off was that I was covering the second model that we will look at, the image classification task. And this one uses MobileNet, pre-trained MobileNet, which is trained on ImageNet. And that one, if you remember, had 1,000 classes. That's why you see here this labels.txt has about 1,000 classes. And if you remember also my joke from last night, it was guinea pig is actually a class. So we're definitely going to run this on my guinea pigs. Just a quick overview again. We definitely need to have our requirements, our dependencies installed of TensorFlow, as well as these options of advising Android Studio not to compress our TF Lite or Lite models. We have a TF Lite model here under app, build, source, main, assets, MobileNet TF Lite. We want to make sure that Android Studio doesn't compress that when it deploys it on our device, either an emulator or a real device, as you're going to see soon. And we went over the code a little bit last night. Again, the idea was, I have a visual here of initializing the interpreter, preparing the input for the model, because our devices, our emulator or real device, can capture it in different width and length and color channel format. We need to prepare it in a way that is acceptable by our model, 224 by 224 by 3 in RGB format. We need to actually call our model. We need to get the results from our model. In this case, will be a long list of 1,000 objects and 1,000 confidence levels. I'm going to pick maybe the top 3 or top 1. I'm going to display that to the user along with a confidence score. Cool. So let's open I have opened my emulator here. I will not run this application on debug mode here in Android Studio. I'll run it as an app. I actually have it installed. So if I click up here, if I scroll up on this Pixel 4 emulator, and if I click on image classifier, and I'll move this in the middle here so you can see a little bit better. And what you're looking at is actually a simulated virtual environment, a VR environment. So this is an environment that the Android Studio team put together. It's a living room. Let me move a little bit. You can move around. So it's like a little game, basically.
Do you know what shoji is? That seems to be a common classification. Not familiar with what that even
I
is.
have no idea what that is. Yeah, but yeah, as you can see at the bottom, as I'm exposing my model to different frames, it's giving me the top class and the confidence level. So for some reason it thinks this is a dishwasher. It's not. Crib, bathtub, maybe. Window, no. How about this? Paper towel, no. Top.
It is interesting that window would often be there. You'd often have a window in a position like that in a room.
Right,
Like
right.
transparent.
Yeah. So yeah, let's move around this virtual environment a little bit. This is like a kitchen environment. I think it's a wardrobe, home theater, electric guitar. I don't know what that.
Now these are ImageNet classes, right? There's 1,000 of them.
There's 1,000 of them, yeah.
So there should be a stove in there, probably.
Yeah. Rocking chair, banister, rocking chair, dining table. Okay, got the dining table part at least. There's a picture of a zebra here. Let's check that out. Envelope, book jacket, no. Crate, no. Wall clock, no. It's not able to figure out the zebra, I guess.
I guess envelope seems like a reasonable misclassification. You could almost imagine, as you're zoomed in there, that you're just looking at a flat table with something laying on it.
Yeah. Okay, let's go back. Yeah, this maybe bookcase, we'll be able to figure that out. Let's see. Dining table. No. So clearly we have some. I don't think it's necessarily the model underperforming because you're going to see it live on real images.
Maybe it can tell that those aren't real books and it's better than we think they are.
Right. But as you can see here, the flow is it's capturing an image from the emulated camera on this VR environment. I can actually step out of the VR environment, by the way. You can go to different rooms. I was surprised it didn't capture the TV. Yeah. We're going to try it live on my phone to see what we are looking at. I'm going to close this. I will share my screen from my phone. Stop sharing. I'll mute myself on my computer so I don't have echo. And my camera. Oh. And let me open my app. Finish classifier. And share my screen with your friends. So this is my image classification app. Can you hear me, Robert? Perfect. You can unmute yourself. I'm looking at my keyboard here, computer keyboard. I'm not sure what that is. I know Lawrence had issues with his sunglasses. I also have, I think it's a mask. My pen, I think was good. Ballpoint, right? That's a type of pen. What else can it be? My camera. Projector, close. Something with Christmas. Oh, I'm glad you picked that. Coffee mug. Let's go to our friends here, right?
Hey girls, how are you doing today? What are you? What are you? Guinea pig? I saw guinea pig there for a second. Can I say it again? Beaver? No. Hamster? No. You are. Oh. The app just crashed. It switches between guinea pig and multiple other. I don't know why it keeps crashing. And other types of animals. How about you? How about I give you some letters? Let us share it now. And let's point it outside. Fountain, no, no. Not the best of luck. Cool. I will stop sharing here. Perfect. So we saw we had some interesting results. Guinea pigs were being classified as guinea pigs or beaver or hamsters sometimes. So that was interesting. Let me share my screen. Robert, you asked me something about one of the classes, if it was part of the labels. What was that?
I don't remember. I guess
Bookcase, maybe?
I saw that it had misclassified a stove as a wardrobe, so I was wondering if
bookcase, bookshop, notebook, comic book, book jacket. Where's the book jacket? Dining table, I think we saw. So dining table should be here. Dining table is here. Oh, shoji or something. Is that what we looked at?
Shoji, yeah.
Shoji. No idea what that is. Travel, ski, sunglasses, right?
Right.
Sunglasses is here. I don't know why it wasn't being picked up.
Okay, so shoji means a
Right.
wooden
Television
sliding
is here
door
too. Cool.
in Japan. It actually looked a little bit like a shoji here.
Awesome. I'd like to move on to the next one. The next one is also pretty fun. So for the next and final, let me close this actually. Model, we'll look at an object detection model that is trained on the COCO dataset. And let me explain a little bit more about this. This is a dataset that Microsoft released back in 2014. Yeah. Very rich dataset. It's not only used for image classification of telling what am I looking at in the image, but also object detection, like drawing bounding boxes, as you can see here. And as well as what is called semantic segmentation, of actually assigning a class to each pixel in the image. So this is a sheep class, this is a person class, this is a dog class. You can overlay that with the original image as well, so you can see how that looks. So this dataset has 80 object categories. You can experiment with it. There's a dataset explore here. We can basically filter by bags, umbrellas, people. Let's look at maybe dogs, food, different household items, and so forth. Just want to look at maybe images of dogs. So yeah, this is doing the semantic segmentation: person, dog, dog, cat, person, dog, dog, and so forth. Cool. So we will look at, again, another app here. And if you remember, under source main assets label map.txt, I have the 80 different classes. This one is probably the catch-all that I'm not sure what it is. So we have person, bicycle, motorcycle, airplane, bird.
Or no, there's question marks all over.
Or maybe cannot be printed. I'm not sure why it's question mark. Potted plant, bed, mouse, book, scissors, toothbrush. So I see 90 here, so I'm not sure. Maybe this is like an extended one, or maybe if I remove the dot question mark, let's see, how many do I have? 11. So yeah, if I remove those, then I have 80. I'm not sure why they're here though. And again, similar, we're going to import tf Lite in our build.cradle here, right here. See that as a dependency, as well as the no compress option. The actual code where this will be running is under tf Lite object detection API. I'll simply want to show you what is slightly different here. So now our model will output, actually I have a slide here that Lawrence explained really well. We'll output 4 things. So our model will output a list or tensor of of 4 dimensions. And the first dimension will be the actual bounding boxes, 4 numbers there, top left, top right, lower left, lower right. The actual class of what is contained, of what the model is looking at. So is it a chair? Is it a dining table? Is it a dog? Is it a cat? The actual score, which is what is the confidence level that our model is predicting a specific class. And the last one will be how many results is the model detecting overall in a given screenshot. So it could, as you can imagine, as you saw in the Coco dataset, you could have a dog, a cat, a person, a dining table, a chair. You can have multiple objects. So this number of results will tell us how many results or how many objects is our model detecting. Is it 1, 2, 3, 5, 10, 80? 80 is max. So this will be just a single number in this fourth dimension.
Multiple instances of any one of
So
those.
in our code now, let me make this a little bit bigger. We need to process our tensors. We need basically variables for our locations where the bounding boxes are, 4 numbers there. What is our class? 1 of 80. The output score, which is the confidence level, and how many overall did we get? That's just a single number. Number of threads using neural network API, some image pre-processing as we saw before, loading the model, reading it from that TF Lite. Let's see. So yeah, that's the main difference. We have basically a 4-dimensional tensor that we need to work with. The camera activity is also a little bit more involved here because we need to draw we need to actually read images, and as well as the UI need to be updated now, drawing the bounding box. I think it's here. But without further ado, I'd love to run this on my virtual Pixel 4a. I'm going to run it on my phone as well. So I'm opening up the emulator, and Android Studio now is deploying my code. As you can see, the install. It's basically installing it like we do from Google Play. And okay, let's see, what are we looking at? So it's detecting an airplane, which is nuts. I noticed there's a little bit of lag in the virtual in this virtual environment. So I'm going to let it sit here for a second. Maybe I'll be updated. It's not a bird. Let me zoom out a little bit. Okay. Sync, no. Sync, no. Chair, maybe here. Bus, no. So we don't have the best of luck in the virtual environment. How about here? It's not able to detect anything. How about our zebra? I was hoping the zebra, this would be okay. I think it's a TV with 50% chance.
That's one of the best predictions I've seen so
not
far.
an air bench. Okay, at least close to bench. Maybe it's wooden. No, it's not able to take the chairs. I wonder why. All right, finally, from this angle, it's able to take the chair. Cool. I'll close this, and I'll actually join from my phone again, and we'll run some live object detections on my phone. So you can see me? Perfect. Share my screen.
Mm-hmm.
Oh, sorry, I need to stop sharing.
Can you hear me?
My computer. And now share my screen.
Can you hear me, George?
Start now. think the app now is frozen. 1 second. Oh, my phone is frozen. Come on. Let's try it again.
Can you hear me? For some reason, it doesn't like when I start sharing and changing it to the app. So let's do this. I will start sharing first. And then run the app. There you go. So we're looking at the keyboard with 73% accuracy, laptop TV, a laptop within a laptop within a laptop. That's interesting. Can you figure out my sunglasses? Toothbrush, kite? No, not a mouse. Dining table, maybe. Toilet, definitely not. Bottle. Where's seeing the bottle? I don't know. There's your bottle. There's our cup. Book. I noticed that Lawrence's
And let's go to our little buddies here. Suitcase, no. Let's see, what does Coco think of you? You're a cat, a bear, a dog. You're not a dog. You're a guinea pig. What about you? Let's give you some lettuce. Lettuce, come here. Come here. Come here, butter. Come here, Kiwi. What do you think of the lettuce? Hey, she took it. She took it. Go over there. She took your lettuce. Your lettuce is here. There you go. Uh-oh. Here comes the troublemaker. Let's look outside my, this is, okay. Bed, it's my bookcase, couch, TV, my live stream setup. I think we had good, let's go by the window actually. For the cars, we had a good detection. Huh? I was able to pick up those behind the trees. Maybe the trees throwing it off. How about the people? Can we identify the people? Yeah, every now and then. Cool. How about me? Can you detect me? Am I a person? I'm a person. Cool. Let me try this one. Person. Cool. Very cool. Okay, I'll stop sharing.
So can you hear me?
Say it again.
Can you hear me?
Yes.
Okay, because I was trying to speak for a while there, and I don't, and you were reacting as though you didn't hear me for like the last 5 minutes.
Oh, I'm sorry. What I'd done is I lowered the volume on my computer so it wouldn't have an echo, and here I had it very low, but I had to put it on my ear. So yeah, I'm sorry.
Yeah. Okay, that makes sense.
Yeah, please tell me. I'm curious to hear your comments.
No, I was just commenting on the classifications themselves. I thought it was interesting that your sunglasses were classified as a toilet, I think, in Coco. And when Lawrence did his demonstration, he got a similar classification for his motorcycle helmet, I think. Just like anything with that round shape, Coco doesn't have that many classes to choose from.
Right. Yeah. So I don't know. Let's see. Does it have sunglasses? Nothing with sun.
He also got tennis racket. That's another round one. I think he had glasses on his table as well. And they were classified as tennis racket, while his motorcycle helmet, which is a round like, bowl-shaped thing, was classified as toilet.
There's no glass. There's no sunglass. There's no helmet.
Yeah.
That's probably the issue here. Yeah. Okay. Maybe people don't wear sunglasses indoors or helmets indoors. Maybe these are indoor items. I don't know, but some of them are animals, right? So there is a zebra. Okay. Backpack.
So regarding the extra classes, I may be wrong on this. I'm sure we could look it up.
Mhm.
I think there may be multiple versions of Cocoa. There were 80 originally, and there may have been some added, and for some reason they're out of order. But the ones that are added were, maybe it wasn't trained with the new additions.
Oh yeah, it says 91 stuff categories, but how?
80 object categories, 91 stuff categories.
How many do I have? I
So
have 91.
you have 91 lines, but 11 of them are blanks, right? So
So what
I
is
think it's the original 80 categories that we're looking at here.
a different
So
color?
there's stuff. If you look at the tasks, or was it data set maybe? I don't.
Overview.
One of them had a list of, must have been evaluate. I'm not sure.
Object detection task addresses things, classes, person, car, elephant. This task focuses on stuff, grass.
Okay, so thing classes might be some countable noun, while stuff classes might be some like collection type noun, where you wouldn't be able to necessarily count how many of the object there are.
Yeah, this one says grass, wall, sky, for example. Oh, so 1 to 91 is thing categories, 90 to 182 is stuff categories, 183 is other category. Semantic hierarchy. Oh, there we go. There's stuff. Sorry. There's stuff. And then there's outdoor stuff.
Yeah, but is this a totally different set of labels here? Are these same items? I don't think these items were in our labels.
Oh, you think so? Sea, river, fog.
Yeah, I think it's a totally different set of labels.
Sea. I don't have sea. River. I don't have river. Got it. So maybe this is a different version of it. Awesome. I enjoyed it. This was fun. I haven't read the paper. Lawrence mentions this awesome application that we've seen in the past, friends, from the TensorFlow team and his district in Tanzania, where they worked with university, I think, and they worked in this cassava classifier of detecting healthy and unhealthy plants. That was a very interesting one. If I can find. This is how it looks like. It would give you a screenshot and it will tell you what type of class the plant belongs to, a healthy or one of 4 disease types. This is one of them, as you can tell. It was an interesting one. This is also in our meetup logo, by the way. This is, I think, how they label the data, I think, and bounding boxes and everything. So that must have been a challenge on its own. What else? That's the same one. I wanted to mention this robotic application or agriculture application where you have this robot that is basically taking images of plants and it's trying to detect where the weeders are. So you see those lights? That's the robot taking images, high resolution images. And then once it does that, you'll see here how that looks like. So that's the front right, back right camera, and that's the top camera. And as it scans, you see here the blue ones are the ones that are labeled as probably as weeds, I think. And if you pay attention, you'll see you see the cameras here, one of the multiple cameras. You'll see some flares actually, and that's the computer using the lasers to actually burn the weeds. See some sparkles. So there's a few, there's a few, there's a few. There's a few there, fire being burned. So it's very precise, basically, a very precise operation. I wonder how long it took him to train it and, you know, operate it autonomously.
Do they give any indication of how accurate it is?
So let's see. You can eliminate more than 100,000 weeds per hour. Accuracy. High power lasers. It's better than pesticides for sure, because you're not harming the actual plant. Doesn't say anything about accuracy. Carbon robotics, okay.
Yeah, 100,000 weeds per hour is great, but it doesn't tell you how many non-weeds it's pulling up to.
Yeah, that's a good point. I don't know. And I don't see it anywhere. Cool. And the other thing I wanted to mention is that Google I/O is happening as we speak, and they have some cool announcements. For example, Android 12 is coming with some really cool look. I like this feature where you upload your image, your favorite image, let's say with you or your family or people you care for, and it'll actually try to detect the different colors, and it will try to identify what is the primary color and secondary color, and it will create a theme based on those colors. So if your favorite photo is maybe by the water and it's blue, your entire phone, your entire theme, the icons, everything will be blue related. If you upload a photo here of a plant like green, you see all the notifications, everything is green based. It's very personalized. I think that was awesome. Workspace more interconnected. I think that's a new feature of Meet, Smart Canvas. Some really, I like how they were presenting the conference. A new projector that basically displays 3D images. I have no idea how that works, but it looks really cool. Look at that. Cameras that are more inclusive of skin tone. Google Photos is creating now animated photos from still shots. So if you have multiple shots, I think we'll try to interpolate what happens in between. It does a good job and it looks realistic. So just from those two shots, it's trying to interpolate what is happening in between and create like an animated video. Photos, you can have like now a locked folder. Passwords, AR view and maps, I haven't used it yet. Privacy-friendly sandbox for machine learning data for Android. That sounds interesting. You can unlock your car now with your phone. Interesting and dangerous at the same time. New health tool to identify skin conditions. I know on my phone I have temperature reading app, as well as a heartbeat reading app that once I place my finger on my camera, it uses light to do those measurements. So it looks like it's doing some more skin condition detection here. Yeah, check it out. It's happening as we speak. Cool. So this was fun. I hope you enjoyed the different image classification, object detection tasks. I really enjoyed the overview that Robert gave with TF Lite. Look forward to seeing you next week, friends. We're going to cover similar models, but now we're going to deploy them on iOS and Raspberry Pi. So it should be a fun adventure. After that, this course has been a little bit demanding, as you can tell, both on software and hardware. So we're going to take a quick break with a happy hour. Hope you can join us on June 2nd. That will mark the end of course 2. And we have 2 more courses to wrap up our awesome adventures. That said, I'll stop sharing here. I want to thank my good friend Robert for joining me in this adventure, as well as my guinea pigs who always keep me company. Cool, friends. With that said, I wish you the best, and we hope to see you next week.
See you next week.
Bye, everyone.